Today's speaker is Yoav Goldberg. He comes to us from Google New York, right? Yeah. Where he's doing his postdoc. Yoav graduated, I think, 2 years ago from Ben Gurion University in Israel. And he's also worked at ISI as part of the summer research program there, doing machine translation. He's done a bunch of different stuff. Today he'll be talking about parsing. And I'm excited to hear this because you guys have probably noticed Google research has been doing a lot of really excellent work in parsing in the past couple of years. So I'm curious to know what you've been contributing there as well.
Okay, thanks. As Mark said, I'm Yoav Goldberg. I'll be talking about parsing, but I'll start with some words about my previous research. So that's stuff I used to work in. So there is parsing there, lots of Hebrew, which may explain my accent, I guess. Some models, syntactic, grammar, prediction, stuff like that. So it's mostly around NLP and structural reason and syntax. This work will be less about Hebrew, but I hope to do more of that later on. So basically, the overall goal, as you may know, is NLP. And what's NLP? It's this process in which you take some text, run it into some semi-intelligent process, and get some sort of meaning out of it. And at Google, we do use NLP quite a lot. And there are three main challenges. So one of them is to use NLP in order to actually do something useful. And for that, you need your algorithms to be accurate. Otherwise, they just not work. But on the other hand, you want to apply NLP to big data. So you want things to run really, really fast as well. Okay, so if I have a very accurate but very slow algorithm, it will just not be scalable enough for us to run. And then there is one challenge that I have a lot of interest in, which is how to use NLP or how to use big data to improve NLP. And that's very interesting, but not in this talk, although I try to do work in this space for a little. So this work is about parsing. Okay? So what is parsing? In case you don't know, parsing takes a sentence and transforms it into a parse tree. So here is a sentence, and here is a parse tree. We're working with dependency formalism, in which each word in the sentence has a modifier which is a different word. Okay? So we basically build these trees which have related arcs, where each node in the tree is a word. And these things can have labels on them, okay? And they do, but I just don't show it here because it's easier to draw and to look at. And the trees are also projective, meaning that no arcs cross over here. If you don't know what projectivity means, it's okay. It's not very important for this talk, but I will use this term. So if I am using this term, it means that nothing crosses, but you can also ignore it if you don't care about that. Okay? And the reason we do parsing is that it's really a useful signal for various other downstream tasks. So in Google, we first parse a sentence, and then we use this as input to some other system. So it can be used, for example, for entity extraction and resolution, for learning new relations, if you want. It's good for answer questions or answering queries, which are sort of questions posed in a weird way. Voice commands, like things like Siri or the new Android kind of voice command interface. And also translation, where you can, if you know what the syntax is, you can translate better. Okay? And the reason we use dependency trees is they're more natural representation for non-linguists or engineers, as I like to call them, to work with. Okay? So that's kind of what we're working with. And currently, there are two main approaches to parsing, or even to just structured prediction in general. And the first one, which I'm pretty sure you all know, is global optimization, where you define a scoring function over a sentence and three pairs. Then you search for the best scoring structure. Of course, search is hard, so you need to make some assumption about your scoring function. And if you make it simple enough, then search becomes simple enough to actually use. Okay? So I will just call that the argmax over some space. Okay? And then, on the other hand, there is this greedy decoding approach, in which you basically start with unparsed sentence, and then you apply locally optimal actions until you are done, and you never look back. So basically, start here, go there, go there, go there, and then you reach the end and you are done. No regrets, and that's kind of a very simple heuristic thing. Just do the best thing that you can at each point. I can call that like while not done, do the best thing. Okay, so it's kind of, it has a kind of a heuristic flavor over there, and well, it is kind of heuristic. So global optimization has some really good selling points. It's very accurate, or it's the best we have so far. It's well studied and well understood, and there's really good foundation to it. Like, so we know hypergraphs, we know line programming, we know marginals, we know various coding methods. There are many things that we know how to do in this search-based space. But it is a bit slow, especially if you want to have rich features. Okay? And it's actually a bit too slow for us still, even if we do pruning all over the place. Just cannot be scalable enough. On the other side, the greedy approach lets you use whatever features you want, so it's very nice. It is very accurate considering how silly it is, and it can be extremely fast. Okay, so if you don't do any search, you can just do things in linear time, but also in a very fast linear time. Okay, so it's you do things in place in memory, you don't copy anything. It can be very, very fast. On the other hand, it is still not as accurate as search-based methods, and in particular, it's very, very little understood. Okay, so there is not much theoretical work there, so you don't know anything basically about the system. You know that they work very well, and you can get them to get you good accuracies, but you don't really understand the systems. Okay, so you just don't know why they work as they do. Okay, and that's a bit annoying, and we would hope to change that. So the main question motivating this work is basically what's the best we can do with the greedy approach. Okay, so I'm not allowed to do search. I'm just doing greedy inference. What's the best I can do under this framework? Okay? And for industry, this is very interesting because, well, you can get good accuracies or better accuracies with the same speed, so you can get better results without paying for more machines to do more processing, which is kind of a very measurable thing and a very easy gain to explain. And for the more academic perspective, I like this because it ties in with incrementality, which is something I really like. So I would imagine that if you think of how a person will process a sentence, it will be much closer to a greedy left-to-right thing than it is to, say, a global optimization kind of approach. So I'm not saying people are greedy all the way, but it's much closer to this extreme than to the other extreme, and I would kind of like to explore what can be done in this extreme. It's also a very cool learning problem. Like, what can you do if you are just allowed to learn one action at a time without doing like full-fledged search? And also, yeah, speed is also something I would like to have. It's nice if your algorithm trains fast and runs fast. Okay? It's useful. So now let's describe how things used to be done when we didn't know how to do them better. So for those of you who have never seen tradition-based parsing before, here is some kind of an overview. It's a bit of a weird story, so bear with me on that one. So imagine there is like this abstract machine which is composed of a stack and a buffer, okay? And this machine is initialized with the words of a sentence, okay? And then we have a set of actions that are applied to the machine and process the words somehow. So they move words from the stack to the buffer, or from the buffer to the stack. They attach words to each other, and they remove words until at the end you are at a state where you have connected words and an empty stack and buffer. Okay? And then you are done. Okay? And the set of actions that you choose to work with define your system. Okay? So there are many possible machines and many possible action sets, and if you choose one particular set of action, then you have one algorithm which you can use. So let me just describe one system, which is the arc-eager system. Okay, so we have 4 operations. The first one is shift. So here we see the stack drawn in gray and the buffer drawn in white, so you don't see it. And the shift operation will take the first word in the buffer, which is B in this case, and move it to the stack. So it will look like that. The left arc action will add an arc between the first element in the buffer and the top of the stack, and we'll also remove the top of the stack. So now things which are gray are not there anymore. They're just drawn there for so you can see them, but they're not on the stack anymore. Okay. The right arc action will do a very similar thing. It will connect the top of the stack to the first in the buffer, and will also push the buffer into the stack. So we move from here to there. And then there is this, finally, the reduce action, which will just remove the first element in the stack, provided that it has a head already. Okay, so we are not allowed to run that if there is no head, because then we'll have a structure with no connection in it. Okay? So these are the 4 actions of the arc-eager systems, and let's see how we can use that to parse a sentence. So here's a simple one: she ate pizza with pleasure. We start by shifting, because that's the only thing we can do. Now we do left arc, so attach 8 to she. Then we do shift again. Now we do a right arc, so we get here. Now we could do a right arc and attach pizza to it, but this wouldn't be wrong. Okay, so it will not be the good analysis. So instead we do a reduce, and then we do a right arc, and then one more, and then we reduce until everything is empty. Okay, and we have a parse, and we have an empty stack and buffer. So that was an example. And now it's a good time to kind of think what we know about this system. So we know basically 3 things about it. We know that every sequence of action will result in a valid projective structure. Okay, so we'll never get a non-projective structure at the end. We know that every projective tree is derivable by at least one sequence of actions. Okay? So we get like soundness and completeness over here. And very importantly, we know that if someone gives me a tree, I can show a sequence of action that will produce this. Okay? So that's called an oracle. And these are 3 essential things we know, and we know them also for other transition systems. So basically, if you want to parse with some kind of transition system, you need to know these things. Okay? So these are the things we know. And these things are quite useful because we can use them to parse a sentence. Okay? So here is basically our parsing algorithm. Okay? So again, we're going to parse she ate pizza with pleasure. Okay? And we start by initializing the sequence from the sentence and the tree. So here is our sequence. Then we initialize the configuration, so empty stack and the buffer over there with all the words. Then, while we're not in the final state, we'll look what the next action is, and then we apply it and move to the next configuration, take the next action from the sequence, apply that, and so on, until at the end we are done and we are out of the loop and we return the resulting tree. Okay, so that's the parsing algorithm. The problem here, of course, is that in order to take the action from the sequence, I need to have the oracle, which is based on the tree, which I usually don't have. So it's not really a good parsing algorithm. Okay, in order to parse, I need to have the final goal, which is bad. So what we're going to do is we're going to think, okay, so maybe it might be that there is a connection between the configuration and the action I need to apply. Okay, maybe they are related somehow. I think it's a good assumption to make, or like a reasonable assumption to make. Okay, so what we're going to do is we're going to replace our oracle with a classifier. So I'll assume like a linear thing, but you can do whatever. So I have this weight vector W, and then what I do is I summarize the configuration as a feature vector. So I kind of look at things in the configuration, and then I try to predict what the best action is based on how the configuration looks. Okay, and then the only question is how to learn correct weights for my classifier. Here is one way to learn. So we start with this parsing algorithm. We make some space here, and then we add these things between. So basically, what we're going to do here is learn or create a training set. So we start with an empty training set. Then we run our algorithm as usual. But after we know what the action is, we look at the configuration, extract features, and then add to the training set the features and the action. Okay? And then at the end, we just train a classifier over this training set. Okay? So that's the batch learning algorithm. I don't really like batch learning algorithms, so I will turn that into an online algorithm. This should be quite easy. Okay? So I'll basically replace these lines where I create a training set with some kind of more dynamic process. So I start with this random 0 weight vector, and then I do my thing as usual. But now, after I have my action, I predict using the current vector. If my prediction is not the gold one, I will update based on the features away from the bad one and towards the good one, and then return W at the end, or an average W, or whatever you want to do. It's kind of standard online learning stuff. Okay? So I guess this should be sort of familiar, or at least the framework should be sort of familiar to you by now. So that's our learning algorithm. And after we've learned how to good weights for W, we can just use this to parse new sentences. Okay, so that's how we do parsing. So to summarize, we summarize the configuration by a set of features, and then we learn the best action to take at each configuration, and hope this will generalize well for the future. And in fact, it kind of works sort of well. So here are some numbers, or some graph with numbers on how well we do in English. So we do quite good in domain. We do slightly worse out of domain if it's a close domain. We do much worse out of domain if it's farther away domain. But overall, it's quite good. I mean, these numbers are really not that bad. They're kind of meaningless because they're not really compared to anything. But I will compare later. Do you want to?
So this is all the same parser trained on Wall Street Journal?
Yes. Yeah.
What would generalization performance look like if you were using a graph-based parser?
The similar trends. All the numbers will be a bit higher, but it's similar. I mean, they all drop on these ones quite a bit. So I don't think there is any preference to one over the other here. I mean, but all the numbers will be slightly higher. So. And of course, you can also do it for many different languages. Here I train each language on its own. And yeah, again, you can get a bunch of numbers, which I'll compare to later, but these are quite good. Okay. And now let's move on to the new stuff of this presentation. So we saw that we can do two things. We can learn a parse from data, and we can parse new sentences. So let's talk about at least one thing we cannot do in this framework, and that's parsing with constraints. Okay, so now parsing with constraints is kind of easy if you have a graph-based, a set-based parser, because you kind of just have a smaller search space. But it's kind of hard in this framework. So let me just explain what parsing with constraints means. So let's know that, let's assume that I know that, say, word 2 is the head of word 7, and word 3 is the head of word 5, or the other way around. And I want to have a parse that will incorporate these constraints. Okay, so give me a good parse, but under the condition that word 2 and 7 are connected. Okay, so how do I do that? Okay, so let's try to see why it's hard. So here are our constraints, and here is a naive algorithm that may look like it might work, but it doesn't. So the naive one is basically start with our parsing algorithm, make some space here, and then add this guy, which basically means says that, okay, so I need to have this constraint. Okay, so if I am at a configuration where word 2 is on top of the stack, and then word 7 is in the buffer, then I can connect them. Then I must connect them, and I do the right action. If it's the other way around, and I have word 3 and word 5, then I do the left action. And if it's neither of these, okay, I will just use my classifier. Okay, so this seems that it might work. Of course, it will fail miserably, and the reason it will fail is that we may actually never reach this configuration. Okay, so if we can connect these two words, we'll do it, but there is no guarantee that we'll actually reach this thing. Maybe some previous mistake that we made kind of just blocked us from getting there. Okay, so that's why this naive algorithm would not work. And this is kind of relates to or highlights some of the things that we don't know about these systems. Okay? So we do know that they are sound and complete and how to drive an oracle. What we do not know, for example, is what is the set of structure which are reachable from any given configuration. So we know that from the initial configuration, we can reach all of the trees. But once we have made some steps, we don't know what is reachable from that state. Okay? We also don't know how an action will affect the set of reachable structures. Okay, so we take an action, what does it mean? Or like in particular, what does shift mean in this context? So I know that like the left arc action will connect to things, so it adds an arc, and I know what it does. A shift will just move something from the buffer to the stack, but it has many consequences in terms of arcs that can or cannot be built, or structure that can or cannot be built, but I have no idea what they are currently, which is a bad thing, I would argue. So in order to bridge this kind of knowledge gap, I will introduce two concepts, and the first of them would be reachability. Okay, and we'll start with a very easy problem, which I called arc reachability. Okay, and that's the problem. Let's say I am at a given configuration, and I want to know, is there a sequence of action after which the edge from I to j will be derived. Okay? And that's very easy because it's very easy to construct such a sequence or prove that it does not exist. Let me give you an example. So again, for this arc ecosystem, let's say I want to add an edge from head to modifier. Okay, so in the easy case, it's already added. Then that's trivial. There is a zero length sequence that can add them. Now let's assume that we have. Now, if it's not the case, then we need to be in a state where we have one of them on the buffer, on top of the buffer, and the other first on top of the stack. Okay, and then we can add the edge. Okay, and of course the modifier, which would be either this or that, should not have a head yet, because otherwise it will violate the tree constraint. Okay, so we need to get to this configuration. Now, if one of more of the item is already reduced, so it's not on the stack anymore, then I cannot do anything. So I cannot add the edge. If they're not on the stack, then I also cannot add, because I cannot move back from the stack to the buffer. Okay, so these are kind of off. Now let's assume like one of them is on the stack and the other on the buffer. Then it's easy. I shift until that's the first in the buffer. Then I do left or reduce until that's on top of the stack. Of course, while I did that, I added many extra edges, which I don't care about. Okay, but let's say it's fine, and then I can add my arc. Okay, so that's kind of one case. Now the only case left is when they are both on the buffer. But that's easy. Just shift until I get to this case, which I already solved. And now I know that I should shift until it's first on the buffer, then add some arcs, and then add what I want. So in both cases, I kind of destroyed all of the middle, but I don't care about that. Okay? Yeah.
So just to make this explicit, you're assuming that every action is always okay if it under this in this language, if it's okay in any language. In other words, there's never anything that prohibits you from linking J to M in this picture.
Yeah. I mean,
some people, when they, in linguistics, if they write dependency grammars, will say, okay, these kinds of parts of speech are allowed to link to these kinds, and those kinds are not allowed to link to those kinds. And you have no restrictions.
Yeah, so currently I'm under this system of transition, and everything which is allowed there is allowed. And the question is, can I have a sequence that will end up in this structure, and I don't care about the middle at all? Okay, and that's what makes the problem easy. Okay, because I don't care about this at all. Okay.
And yeah, just to clarify, at this point you're simply talking reachability. You're not asking what is the most likely sequence of actions
No.
that will result.
Yeah, is there a sequence that will do that? Yeah.
And then one can build on it and say,
Yeah, but
that sequence likely and so on.
yeah, but now I don't have any weights or anything. Just like the system, can I reach this or not? And just reason about the system as a system. Okay. So to summarize, these are the rules. You can verify that they are very easy to check. Okay, I can in fact check those in O of 1 and a very fast O of 1. Okay. And so that's kind of.
But depending on how far away these things are.
No. So these are the rules, right? So like if the arc is already there, then it's okay. And this is kind of a hash lookup.
And was not assigned that took care of that one where it wasn't.
Yeah. And then I need either both M and H are on the buffer, which is easy to check, or one of them is stuck and the other is on the buffer, which is also easy because I can track what I have where.
The scanning was just to demonstrate to us that there is a.
Yeah. So yeah.
But checking is simpler.
Yeah. Okay. So that's very simple to check. Okay, it's all of one, very, very simple checks. And I can come up with a similar kind of scanning thing for any system, basically, and it will always do kind of like a very easy solution. Okay, so this is kind of an easy problem. Of course, it's not really an interesting one. And the more interesting problem is what I call the arc set reachability, which basically states, so I'm in a configuration, I have a set of arcs, can I derive all of them together? Or can I have a structure with all of them? And that's a much harder question to answer. And it's harder because, well, that one was easy because I didn't care about the interactions. Okay, I was just able to build stuff and just to get to where I want. Here I really do care about the interaction. Okay, so I want to know if these things can kind of live peacefully together. Okay. So this is a much harder problem. In order to solve that, I will introduce this new property, which I like to call, well, like is a bit of a strong word. I don't really like this name, so I'm looking for better names if you could find them for me. But this property, which I call arc decomposition, okay? And this property is a property of systems, of transition system, which states that if a set of arcs are individually reachable, then any subset of them which can be extended to form a valid tree is also reachable together. Okay, so that's kind of a very strong property, but it's a very nice one. Okay, it means that if I can reach all of these, then I will also be able to reach all of them together. Okay, which is a very nice thing to have. So one sad consequence is that the arc standard system, which is a system I really used to like, is not decomposable in this sense. Okay, so there, if I can if I can reach two arcs individually, there is definitely a case where I cannot reach both of them together, because that's a very easy counterexample to show. On the other hand, the good news is many other systems with the arc eager system and the arc hybrid, which is very similar to the arc standard, and the easy first, which is mine, are all arc decomposable, okay, for which this property does hold, which is very nice. And this property basically allows us for many systems to reason in terms, or to work in terms of reachable arcs, but to reason about reachable structures, which is much more interesting. Okay?
So yeah, the first claim is actually a little tricky, right? What you're saying is that there is a set of arcs which are all individually reachable, and there's a subset of them which is even consistent with a projective tree.
Yeah.
And yet, that set is not reachable. And there's a configuration from which each of the individuals are reachable, and the set is not reachable.
Yes. And
just draw it on the board and satisfy our curiosity.
yeah, where is the board?
Right.
Oh, that's okay. So for the ARC standard system, if you know it, then great. If you don't know it, just believe me. Okay. So let's assume that's the configuration. So we have the stack with 3 items. Okay. So this arc is reachable by adding this arc and like removing this guy, and then adding that arc. Can you see from there? It's all good. This arc is reachable by just doing this left action, but you cannot reach both of them together. Because in order to reach this one, you have to move the other one. Okay, so that's why it doesn't work for the ARC standard system. But we can prove that this will never happen for the other systems, which is a nice thing to know about them. And this basically gives us an algorithm for ARC constraint parsing. So for any ARC decomposable system. Okay, so if our system is ARC decomposable, basically if we have a constraint set which is projective, meaning basically that it's satisfiable, so there are no kind of conflicts in our constraints, then if we can derive all of the individual arcs in the constraint set, we can derive all of it, which is good. So all we need to do is stay in configuration from which all of the arcs in the constraint sets are reachable. Okay? So it's very easy to define this set of allowed action with respect to configuration and some arcs. Okay? And so it basically goes like that. So you are in a configuration, you apply the action, you see your new configuration, and you check what are the reachable arcs from that new configuration, which is easy to check. And if it's a superset of the ones you want, then this action is allowed. Otherwise, it is not. Okay? So this is kind of a declarative definition, but you can believe me that there is a very efficient way to just implement that as queries. So I can ask, is this action allowed or not in this configuration with this set of arcs, and I can get the answer very, very quickly. Okay? But that's the set I am interested in. And once I have this set, I can actually have this arc constraint parsing algorithm, which is basically the parsing algorithm as before, with this addition that if my action which I chosen is not allowed in this configuration and with these constraints, I just choose the next best prediction for my classifier. Okay? And it's kind of easy to show that first I can do this very efficiently, and also that if I have good constraints, which are kind of just consistent, then this set will never be empty. Okay? Just kind of by definition, actually. And I will always be able to find a good action. Okay? So what do we have so far? We can calculate the reachable arcs from any configuration. Kind of easy to do. We define this property which holds for the arc eager system, and we have an arc constraint parsing algorithm which holds for any system for which this property holds, in particular the arc eager system which we actually use. Okay, so that's kind of a nice thing, but I think we can do more than that. Okay, so let's see what else we can do with this knowledge of how the system works. So for that, let's just take one more look at training. Okay, so here is the training algorithm, and one thing I don't like about it is this line. Okay, and this line is bad because the oracle will produce one static sequence. Okay, one single sequence of action to follow, but in practice there may be more than one sequence of action that will lead to a goal tree. Yeah.
Well, I have a question sort of before we move on
Sure.
to this last point. So this kind of goes back to what Sanjeev was talking about with the fact that you're not free to, in the future, you're not free to choose any sequence of actions. Like you have a static policy, right? And so you're going to be choosing. You're going to be scoring these actions and choosing the top action.
Yeah.
And so I guess the question is, it seems like you could have ruled out some actions earlier by saying, okay, at this point, if I was to choose the top action, actually, maybe I'm seeing that this won't happen. So I guess the question is, if you were to say score a sequence of actions by, I don't know what it would be, the sum of the model scores at each time step, doing what you're doing, your way of constraining things, is that guaranteed to say produce
the most likely thing? No, it's not. So under this kind of greedy regime, it's really hard to guarantee any kind of optimality in the future. And it's up to the training to try and produce a good result in the future, okay? Because you're not allowed to search, you're not allowed to change anything, and you just kind of have to get like good kind of heuristics on what the future is going to be like, if you want that. Okay.
Actually, can you back up? I also had a question on the previous slide. Can you back up?
This one?
So this thing about the allowed actions is never empty.
Yeah.
Right? You'd have to essentially ask if in the configuration where the entire string is in the buffer and nothing is in the stack, you would have to ask whether there is any allowed action. Because right there, if there is no allowed action, it means A is an inconsistent set of
Yeah, I think you mean the other way around.
and you would stop.
Everything's on the stack and nothing's left in the buffer.
No, I
No.
think.
Before you, in other words, how do I know whether A is a decent set?
Okay, so yeah, so if A is projective, okay, so I assume that the user gives you a set which is projective. If you want to actually verify that it is projective, I think it's a cubic algorithm.
Right. Actually, I was concerned about that, to check whether A is actually projective. And what I was thinking is that...
No, actually, it is actually very, very easy to also check that. You just kind of connect all of them together and see if you can build a tree on top with everything else allowed. And it's usually, it's very easy to, it's easy to verify. I don't have the algorithm, but it's easy. Like if you have just one allowed head for each word or all of them, it's very easy to see if this is projective or not. Okay?
One thing you can do is use a graph-based parser, for example. This is only at training time.
no, this is not just a case.
No, that's at inference time, but this question is actually much easier than the one for which you need actual inference, because you know that so your constraints allow or either a single or all of the words for each. Okay. Okay. Yeah, so the next thing. So as I said, this thing is bad because we have what we call spurious ambiguity. So let me give you...
In the ARC standard, right?
What's that?
In the ARC standard, is there still spurious ambiguity?
Yes, there is.
Is there?
Yeah, I can show it to you later. So let me give you an example of that. So here's a sentence. He wrote her a letter. So we start by shifting left, shift, right. And then we can do either a shift or a reduce. Okay? And then we can do either a shift or a left. And then we can do either left or reduce. And now we're kind of in the same state in both configurations. So we just continue to the right. And then we're done. But now we have to kind of ask ourselves which sequence is better. Okay, so well, they are both equally good because they both got to the correct answer. So they are both equally good. Maybe want to ask like which sequence is easier to learn. Okay, if I'm trying to learn these things. And what people usually currently do is they create oracles in which they always prefer a shift if you have a shift-reduce conflict. Okay, and the reason they do that is that they tried both ways. And one of them was mostly slightly better than the other. Okay, so kind of like just see what works best and then stick with that. Okay, so it's kind of a good way to go about it if you just want to have good accuracy. But maybe we should just let the classifier choose either of them based on context. So I don't want to say that I always do this for that. I just like see what's most natural to me and then use it. Okay. And basically what I want to do is replace these two lines in the algorithm with this, okay? So I don't have a sequence anymore. I have this like oracle object, okay, which is initialized based on the sentence in the tree. And now after I have a prediction, I ask, is it allowed based on the oracle? So kind of like dynamic query. And if it's not allowed, then I take my goal to be the highest scoring allowed one and update toward that. Okay, so I no longer comparing to a static single action. I am comparing to a set of actions. Okay, and I update toward the best allowed action in this set. Okay, so that's the new training algorithm. And of course, the question is, okay, but how I can find this oracle that will tell me what is allowed and what is not allowed? Okay, and actually now I have a very simple answer for that. That's just a very special case of our constraint parsing with very extreme constraints. Okay, so basically we need to make sure at each stage that the goal tree is reachable. Okay, so this basically means that we just take the set of allowed arcs to be all the gold arcs. Okay, so we have a very kind of strong set of constraints, but it will allow all of the paths that lead to the goal tree. Okay, and I have already an algorithm for that, so that's kind of easy to solve. Okay, and as a bonus, this also works if I have only a partial observation as my constraint. So now I can also kind of train with a partial constraint set, which is not a full tree. So that's kind of a new thing that I can do now in this framework, which I got for free just by changing how the training works. But let's assume that I do train with all of the gold arcs, okay, so no partial constraints. Actually, it works pretty good. So I get some improvement across all data sets, almost. Okay? There is a slight drop here, but I would not count this as a drop. So there is kind of a consistent gain across all data sets. The numbers are kind of what we would expect from a small change in a parsing system, slightly better, but like nothing spectacular. So 0.5 max improvement, quarter point, average improvement. So it's kind of consistent and nice. And it seems to work pretty well. If you move to the like multilingual setting, then it sometimes works very well. Sometimes it works less well, and there is some drop in Chinese and a large drop in Hungarian. I have no idea why there is this drop in Hungarian. If anyone here speaks Hungarian and would like to help me analyze the result, I'd be happy to. But basically, if you want to like sum this up, it's mostly beneficial. Okay, so it's nice to kind of train with this ambiguity allowance. But we're not there yet. So now let's take one more look at our modified training algorithm. And the other line, or the other part I don't like about that is this part. Okay, so this part basically means that if I made a mistake, I choose one allowed action and I use that. Okay, and what this means basically is I always follow a correct action, and the training algorithm will never see configuration that resulted from incorrect actions. Okay, so you might ask, okay, so why is that a bad thing? And that's a bad thing because the training is attempting to learn the optimal action for each configuration, but there's also kind of an assumption here, which is that all of the previous actions were correct. Okay, so in training, I'm kind of having this scenario in which I made many good predictions, and now I need to make one more prediction, and what's the best prediction is. But of course, in parsing time, we may make a mistake. Okay, and after we made a mistake in parsing time, this assumption that everything was true up to this point no longer holds. Okay, so we may reach a state that we haven't seen before, and then we'll have no idea what to do, and we kind of generalize from other states completely. Or we may reach a state that we have seen before, but under a different assumption, and maybe there is something better to do here if we assume that we may have got here due to wrong reasons. Okay, so we really do need to account for that. So the underlying thing is basically always try to make training conditions as similar as possible to testing conditions. That's a good rule to follow if you want to just take one sentence from this presentation. Yes?
So maybe it's worth mentioning Dagger here.
It's very similar to Dagger. I'll touch on that in the future. So what we need to do is to expose the parsers to configurations that resulted from bad decisions or from errors. And also, I need to tell it what is the optimal thing to do in this configuration. And basically, that's the hard part, okay? Because it may not be clear, actually, what is the optimal thing to do. Okay, so I made a mistake. Now I should do something, but what should I do? Like, I should do the best thing, and I don't know what the best thing is. But let me try to give you a reasonable definition of what the best thing is, or at least something which I think is reasonable. So it's basically this definition. So if the goal tree is reachable, so I haven't made any mistakes, I want to reach the goal tree. That's kind of given. And if the goal tree is not reachable, then I want to be able to reach the best reachable tree. Okay, so I cannot reach my goal, but maybe I can reach a tree which is very similar to it, and then I want to reach that. Okay. So what's the best reachable tree? It's basically, in my definition, is the tree with the with the smallest Hamming loss to the goal tree. Okay, and
Can I ask you a question, though?
yeah, sure.
I'm confused by this. So you're saying that there is a sequence of actions, and I'm thinking right now where you produce a single oracle sequence of actions, right? And then you say you made a mistake.
Yeah.
The goal tree is still reachable.
No, no.
This must be one of those spurious ambiguities, right? Because otherwise, a mistake would mean that the goal tree.
Yeah. So no. So this actually means no mistake. Okay.
Okay.
Or like either mistake with ambiguity or no mistakes. So let's assume there is like no mistake here. Yeah.
So in other words, when you make a real mistake, the goal tree is no longer.
Yes. Yes. Okay. Because that's how I define mistakes. Okay. But if I made a mistake and the goal tree is not reachable, I want to reach the best reachable tree.
The minimum Hamming loss.
Yeah, or the minimum Hamming loss. Basically, the tree with the most gold edges which are still reachable.
So now you look, okay, so at least naively it looks like I'll have to enumerate all the trees reachable from this erroneous state and then choose them.
Yeah, but so actually, fortunately, because I have this arc decomposition thing,
Right.
okay, I can just take the union of the goal tree and the reachable arcs.
I see, just treat it as a set.
Yeah. Okay? And then, because I know that everything that can be built from this arc is reachable as a tree, I know that the best tree, okay, is there. So that's kind of the neat trick over here. And actually, a very small tweak to our oracle will make it behave optimally for any configuration under this optimality criteria. And it will also allow us to return a cost for each action at a configuration. So for each action at a configuration, I will know exactly which arcs are no longer reachable, which is a very nice thing to have.
The first time or any time you make a mistake, based on your past actions, you know which arcs in the goal tree you lost because of the mistake.
Yes.
There are others that you got, and then of the remaining, you just see which subset is the reachable.
Yeah.
Or rather, which.
Okay.
And you have to test them only one at a time.
Yes.
Because if they're reachable one at a time, then that's the set A, and then any
Yes.
subset including A itself.
Precisely. Okay. So just kind of to slightly elaborate on that. So I'll define the cost of an action at a configuration to be the number of gold arcs that are reachable from a configuration, but are not reachable after taking the action. This is very easy to calculate. And then under this definition, optimal actions have a cost of 0, and there is always, by definition, an optimal action with a cost of 0, okay? Because it's kind of the way it's defined. And here's like kind of a quick quiz. Basically, let's assume that in the gold arc, in the gold tree, there is no arc between a head and a modifier. Is there an optimal action that will add this arc? And the question is yes, there is. And it basically means that like if I made a mistake and I cannot find the right parent for this modifier, I might as well choose a different parent if it doesn't kind of break other things down the line. Okay, so it's kind of maybe a bit counterintuitive, but kind of that falls out of this system, and it is correct. Okay? So basically what I'm going to do is I'm going to change or replace this line with this. So sometimes I follow the gold action, other times I follow the one which I just which may be wrong. and now my oracle is optimal, and it will give me the best thing to do if I'm wrong. Okay, so now I kind of do this kind of exploration in training. And if you kind of know the CERN algorithm or the Dagger algorithm, then this should look very familiar to you, okay? And it should, because basically our new oracle, which is optimal for every configuration, is a very good policy in the CERN sense of what a policy is. Okay, and earlier attempts to use CERN for parsing failed just because they didn't have this policy component. Okay, so now there is a policy component, and it actually, I definitely believe that using CERN with that will work, but my algorithm is very, very similar. It's actually, you can see my algorithm as like an online Dagger thing, which I kind of believe have the same guarantees as Dagger. I just didn't prove it yet, but it should be very, I mean, I don't really care about proving it, but if you want to prove it, go ahead. I'd be happy to see a proof. Anyways, if you do that, that kind of training, you get really kind of nice improvement in scores. Okay, so here it's actually something which is really visible. So we get an average improvement of 1 point, max improvement of 1.4, which is really kind of meaningful. Actually, the numbers are slightly higher. These are kind of results with a bug, and I was lazy to change the graph, but results are a bit higher. It's nice that the bug actually, like fixing the bug, actually got the result to go higher and not lower. That's a nice thing about the algorithm, actually. Correct. Yes?
So what types of practical things or the greedy plus the ambiguity?
So it basically corrects things across the board. I mean, it's kind of hard to kind of pinpoint just one kind of mistake that it is better at. One kind of mistake that is much better at is like root attachment. So it's make much less, many fewer root attachment mistakes. But also many other kinds of mistakes are just better, but I cannot say like a particular one. It doesn't quite help with PP attachment. But it basically helps across the board. Yes?
So I'm going to assume that because you're doing more exploration, you're creating new features during training, so it's probably slower than the original version? It has more in memory? It's got more stuff to consider?
It is a bit slower, but not by a substantial amount. I mean, we have more features, and we have a larger feature vector. But if we have the same feature set for both models, then the difference is kind of very negligible.
If you do use the same feature set, do you still see the same gains, or is this a matter of?
These are with the same feature set. Okay, I didn't change feature sets here.
Oh, if you do like include new features from configurations, during your exploration phase, you might see even larger gains. Like I think the same thing happens in graph-based parsing, where.
So I don't really. It's the same feature templates, okay, which may produce many more features. Okay, but it's the same kind of set of like whatever templates I'm using. So there are like newer features, but they are not kind of newer kinds of features. Okay. So yeah, nice results here. Also for other languages, I get very similar gains. If something kind of drops for Chinese, you get it back up, so it's nice. Hungarian, still annoying. But less so. Actually, in the new version, this gap here is much smaller. So Hungarian now is kind of still a bit worse, but like really by a tiny margin after fixing my previous bug. But still, I mean, it's annoying that it's not there, and I would like to know why Hungarian behaves so badly. But overall, this thing works. I mean, these are really nice results in my view. So just to kind of sum it up, concrete things we now have is we have parsing with arc constraints, which I've shown you. We have in a kind of different work parsing with span constraints, which is a bit more tricky, but in the same kind of spirit of things. We have this oracle, which is optimal for every state and can work with partial observations. So we can actually train with partial observations. And we have more accurate deterministic parsing, which is kind of a very nice new result. And if we think of what we didn't know before, and now we can actually answer these questions. So how does an action affect the set of reachable structure? Well, for these arc decomposable systems, it will remove all the structure that contain the set of arcs which are lost by the action. Okay? And what is the set of structures reachable from any configuration? Well, it's the all of the structure which can be built from reachable arcs. Okay? And what does shift mean? So in the arc ecosystem, shift basically means the token on the buffer is done with all of its left modifiers and is really expecting ahead to its right. Okay, so now we kind of really know what is going on with the shift operation. There are various things we can do with this, but I do not want to limit your creativity, so I'll skip that. And I'll let you read this take-home message where I take questions. Thanks. Yeah?
So I don't think you showed results for this. So when you first introduced these constraints, I thought you were going to go to the setting where you had constraints on the parse, and then you were going to parse. I mean, you use them for something else, but have you looked at applications where you do have constraints that you know from outside of the parse and that you can actually use this?
Yeah, we do have these kind of applications. At Google, it's kind of harder to measure them. But let's say we have a very good entity recognizer. So we know that like some spans must be entities, and we just want our parse to be consistent with that. So now we run this span concept algorithm, and we get that for free, basically. For our constraints, there are some situations, maybe a bit artificial, but say in Japanese, if you know the bunsetsus, you know several arcs, so we can just use that and do it. In terms of training with arc constraints, I started to explore that, but I don't have any concrete results yet. But basically, the motivation for the constraints was various things that we do at Google, which are harder to measure, but we just need things to be consistent.
So, well,
I have a question. Could you go back to the last algorithm-like slide where you were looking at this one? Right?
Yeah.
So sometimes you do something, sometimes I guess this involves some kind of sampling, right? Are you doing, or are you doing it something deterministic?
So I can just tell you what I do. So basically, in the first round of training of the training set, I just always take the one I predicted. Okay. Sorry, the gold one. Yeah, just to kind of get to a good state. After that, I basically flip a coin, and 90% of the times I pick the one I predicted. So it's mostly exploration. But of course, the one I did predict might be correct. So I mean, and changing this number doesn't really affect the score that much. I mean, if it's much lower, so if I hardly do any exploration, like if it's 0.2 or 0.3, then it's worse results. But if it's around 0.9, 0.8, 0.95, even 1, I get very stable results there. So it's kind of, you should explore as much as possible, basically.
The reason I ask is because I was thinking of two alternatives to what you just mentioned. One was to, like, your predictor probably gives you some probabilities on the actions, not just that this is the best, this is the second.
Not really, but it could.
Okay, it could. So I was thinking one that whether you would sample based on that, saying that if the correct action is highly likely, then you just sample, basically sample according to that probability distribution, and so most of the time you'll be sampling the correct action where it's going to be chosen, and incorrect one just frequently.
Yeah, so it's sort of similar because I choose the action, like the gold action, which is the most highly ranked by my current scoring function. So it's kind of more deterministic than what you suggest. I just never choose the lower ranked one, but it's very similar.
The other thing I was thinking is that if you're in some situation where the domain you're going to parse and the domain on which you're training are mismatched, and you have a little bit of parse data in the new domain, whether you could look at error statistics from the new domain and use that to do your sampling so that you're matching your parser's training in erroneous states more to what it will see in the new domain.
That's a very good suggestion, and I kind of thought about that, but I don't have anything concrete there yet.
Do you have some sense of which are the most problematic decisions in this setting, or the most problematic that this one corrects? I know in answer to another question from Adam, you said that the improvements are all over the place. Was this?
I do not have a good answer to this one currently, but I am looking at kind of what's happening there. But I don't have anything kind of concrete or meaningful to say at this point. I will have in the future. So.
I mean, I know from talking to my parsing friend, I'm not a parser, that these PP attachments over long distance are a problem, and then coordinated injunctions are often problems.
Yeah.
Does this uncover that?
This uncovers some kinds of, I mean, we do see gains in conjunctions, but I mean, we also see gains in other things. As I said, the PP attachment is less solved by that, but that's because, well, in this system, when you commit to a PP attachment, you cannot really recover from that.
I see, you can just do things having made a wrong attachment.
Yes.
Which actually might often be easy to do anyway, because it's just a high-level attachment that's wrong.
Yeah. So like basically, if you decided that something is a determiner, even though it's like a relativizer, then you can just ignore that and add one more determiner and do something on top, which is kind of.
All right, thank you.
Yeah.
So this is just a thought, but it occurs to me that one of the things you might also be able to do here, now that you have this way of essentially saying, in the future, is it possible for me to generate some particular art? You could also use that as a heuristic cost in the A star sense. So you can now answer questions like, what is, with respect to maybe local features of arts, maybe give some heuristic future cost. So when I'm deciding on a particular action, I'm deciding not just on the history, but some simple heuristic of a possible future stance.
Yeah, it's definitely very interesting, and I did think about that. Like basically, have some scores for all of the possible arcs, and then base that in heuristic. The problem here in Google setup is that this will actually require you to look at all of the arcs, which is again expensive. But I do want to look at that like in 2 months when I leave Google. And
so maybe you could do this in sort of conjunction with sort of like other work going on at Google is vine parsing stuff that's up and running.
Yeah, it's.
Consider them within a beam or something.
Yeah, definitely. I mean, yeah, there are many things which you can do, and I will definitely. Yeah, we should talk about that more.